Frightening declarations by astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They recommend that this frosty world is on a potential crash course with Neptune. But how could this happen, and what might the outcomes of such an enormous event be? Are we seeing an intriguing cosmic peculiarity, or is there something else to this approaching grandiose impact? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet mostly because of its exceptional orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is hazardously close to Neptune's. Tyson and Kaku are raising the alarm about a potentially dangerous impact between these two celestial bodies, which could pose an immense risk to Earth. But how is such an event even conceivable? Pluto's orbit around the Sun is unlike any other planet in our solar system. It requires a stunning 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. The interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, straying significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unconventional is its tilt, calculated at 17 degrees to the ecliptic plane. The way Pluto follows its orbit is much more inclined compared to the other planets, adding layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to understand its unique trajectory. Unlike other planets whose orbits lie somewhat near the ecliptic plane, Pluto's path stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacy of space mechanics. The three-body problem in space is about figuring out how three bodies, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms hub vibration, scope libration, and VSK oscillation are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is pivotal vibration. In the case of Pluto and Neptune, this means that when Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune, or any other giant planet, it is arranged mostly above their orbital plane, providing an additional layer of protection from potential collisions. Another key factor in this equation is the VSK oscillation, named after three researchers, von Zeipel, Loff, and Kazai, who studied how objects move in space. This oscillation describes how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity, influencing their movements. For Pluto, the VSK oscillation helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit seeming erratic, this oscillation helps keep it moving smoothly over long periods. These factors work together to keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or get thrown off course. The three-body problem helps us figure out how these orbits change due to the gravitational interactions of space objects. Studying this helps us learn more about Pluto, our solar system, and distant worlds. Mathematical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is actually chaotic. Minor deviations in initial conditions can lead to significant differences over millions of years. However, the unique properties of Pluto's orbit have been found to maintain stability over incredibly long time frames, effectively keeping chaos at bay. Recent computer simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique connection with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit consistent. However, Neptune isn't the only planet at work. Jupiter's gravity also plays a major role in stabilizing Pluto's orbit, with Saturn contributing as well. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady path for a long time, possibly even billions of years. Maybe Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are essential in maintaining the order and consistency of celestial bodies' movements. Without these mechanisms, our solar system would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, triggering a cascading chain of events impacting other celestial bodies. For Pluto in particular, with discussions about it potentially crashing into Neptune in the future, understanding its orbit is crucial to giving a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can reach a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can dramatically alter its long-term orbit. Using computational simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on each other. By tweaking small details in the simulations, astronomers can see how even minor changes can lead to significant differences in Pluto's trajectory. Back in the late 1980s, these simulations uncovered something interesting about Pluto's orbit. Even with factors like axial tilt and orbital libration keeping it steady, its orbit can still be very wild and unpredictable. If you start with just a small difference in Pluto's initial position or speed, its orbit could end up looking very different over many years. But even amidst this chaos, Pluto's orbit remains stable over incredibly long timescales, suggesting that its journey around the Sun follows a type of order despite appearing chaotic at first glance. Looking ahead to cosmic events, especially those involving chaotic or eccentric orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term predictions are often fraught with uncertainty. While mathematical simulations provide great tools for understanding and predicting the future paths of celestial bodies, they also highlight the limits of our forecasting abilities. These models heavily depend on the accuracy of the starting conditions and the complexity of the interactions they simulate. Any small error or misrepresentation can lead to vastly different outcomes, making precise predictions difficult. Moreover, the chaotic nature of celestial orbits like Pluto's serves as a reminder of the ever-evolving and dynamic universe. While we've made significant progress in understanding space, Pluto's case exemplifies how much we still don't know about the cosmos. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have substantial effects on the stability and trajectory of other bodies within the system. So why are major astrophysicists just now raising concerns about a potential collision between Pluto and Neptune, despite all the complex forces working to prevent such an event? Tyson offers an intriguing perspective on the mysteries of our solar system, especially the fascinating case of Pluto. Known for promoting astronomy, Tyson views the renaming of Pluto not as a downgrade but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of constant learning and evolution. Tyson sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The allure of these questions, according to Tyson, is what makes astronomy so captivating. He keenly understands how space events and discoveries shape public interest in space science. He believes that events like Pluto's renaming or its orbital peculiarities can captivate the public's imagination and spark curiosity about the universe. Tyson, along with other researchers, warns the public about the potential risk of Pluto's erratic course. After studying Pluto for years, he has raised concerns that the three-body problem could pose a significant risk when it comes to an impact with Neptune, an event he suggests may be long overdue. He emphasizes that such a collision could completely alter the balance of the universe and trigger devastating consequences reaching as far as Earth. If Pluto and Neptune were to collide, it would be an intriguing and catastrophic event in our solar system. The crash would release a massive amount of energy, potentially breaking Pluto apart due to its smaller size and icy composition. Debris from the collision could spread across the solar system, possibly creating hazards for other planets and their moons. For Neptune, such an impact could alter its atmosphere and potentially its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory and as a popularizer of science, brings a unique perspective to this discussion. His views on the future of space exploration and the interplay between celestial mechanics and theoretical physics provide deep insights into the mysteries of space phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a window into the future of space exploration. He believes that understanding the complex gravitational relationships and orbital elements of celestial bodies like Pluto can offer vital insights for future space missions. This knowledge can help in exploring the solar system more effectively, predicting potential dangers, and even planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. When discussing the physics of planets, Kaku often highlights how celestial mechanics and theoretical physics are deeply intertwined. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated phenomena. They are connected to the fundamental principles of physics. Kaku's work in theoretical physics, especially in string theory, seeks to understand these principles at the most fundamental level. He often suggests that by studying the intricacies of celestial mechanics like Pluto's orbit, we can gain insights into the underlying laws of the universe. Similar to Tyson, Kaku has warned about the looming impact, connecting it to his theories about the universe. If Pluto and Neptune were to collide, it would be a major event in astronomy, offering a unique observational opportunity that could intersect with string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. A collision of such magnitude in the solar system could generate extreme conditions of energy and gravity, possibly creating scenarios where phenomena predicted by string theory could become observable. For instance, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme conditions, key areas of interest in string theory. Additionally, the gravitational waves generated by such a collision could provide valuable data for testing predictions from string theory related to gravity and spacetime. These waves might carry signatures or anomalies that align with or challenge the predictions of string theory. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific ramifications of such an event could be immense, contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit is a beautiful example of celestial mechanics at play, showing both stability and chaos within our solar system. The unique qualities of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the unpredictable and dynamic nature of space. The three-body problem is not the only mystery of the universe we have yet to solve. Many other potential disasters are expected to occur in the future. While the possibility of planet impacts in space is truly fascinating, it cannot be entirely ruled out. The dynamics of planetary orbits can be affected by various factors, including the gravitational interactions described by the three-body problem, in systems with multiple planets, such as the TRAPPIST-1 system, which contains 7 planets about the size of Earth. These planets can pull on one another with their gravity, creating a rhythm or pattern in how the planets move, known as orbital resonances. The study of Pluto and its interaction with Neptune provides us with a deeper understanding of the delicate balance within our solar system. Even though Pluto's orbit appears erratic, its motion is governed by subtle gravitational forces, and the long-term stability of this orbit is a testament to the intricacies of celestial mechanics. This insight extends beyond Pluto and Neptune, as it underscores how the gravitational influence of all planets within our solar system plays a vital role in maintaining order. In this sense, the solar system functions like a well-oiled machine, with each celestial body exerting its own pull to ensure the system remains cohesive. Theoretical physicists and astronomers alike are continuously exploring ways to predict the behavior of celestial bodies in more chaotic systems. By examining systems like Pluto and Neptune's orbits, researchers can refine models to apply to even more distant and complex systems, potentially extending their reach beyond our solar system. New technologies, such as advanced telescopes and AI-driven simulations, are enhancing our ability to detect and track the movement of distant objects, making it possible to foresee events in the cosmos that were once thought impossible to predict. Understanding the gravitational dance between celestial bodies is also critical for future space exploration. With an eye toward missions to outer planets, moons, and exoplanets, the knowledge gained from studying Pluto's unusual orbit could inform decisions about spacecraft trajectories and interplanetary navigation. The more we learn about the forces at play in our own solar system, the better equipped we will be to explore the vast and ever-changing universe that lies beyond.